Alrighty, so we got two different types of solids, crystalline solids and amorphous solids. And so the difference being, one is regular and repeating, the other one is just put together. Now, we get a lot more information from the crystalline solid, and in actuality, we look at crystalline solids quite often because most of our ionic compounds fit within the crystalline structure form. The amorphous solids tend to be solids that are molecular in nature, and we get a little bit less information from them. And so, if it is crystalline, all right, what we get is a piece of information called the unit cell. Okay? And so in a crystalline solid, we have a repeating pattern. And so we don't need to know the entire entity of everything that is there. We just need to be able to understand the smallest repeating unit, which is what's called the unit cell. If we understand the unit cell, then we understand the totality of how everything is put together. And there are three main ways in which packing occurs. These are the simplest ways. All right. There are other ways, but these are the three simplest and what you learn at this level. One is primitive cubic, where there is an atom represented at each one of the corners. There is a body-centered cubic. Why in the world do we call that one body-centered? What's in the center of this one? Do you see? There's a whole something inside the middle. It's inside the center. And so if you count what's inside, here on the primitive cells, only a part of this atom's on the inside. And only a part of this atom is on the inside of this cubic entity or that space. But inside here, that one atom or something is totally inside, plus parts of each of the corners. Okay? The next one is called face-centered cubic. Why in the world is it face-centered? Because on every face of the cube, there is one sitting there. All right, there's one on each of the corners, and there's one on the faces. Which one of the two has more inside the box? Is it the corners or is it the face? The face, okay? And so each of them have a value that is inside the box and outside the box. Now, we show these in small little round balls, but really they take up the full volume of space. Something you need to know, this packing right here is the most compact packing that you can have, called face-centered cubic. And so you get more stuff in the space, which would make it more dense, ultimately. Okay? Now the types of bonding in crystalline solids, they're right next to each other, so it depends upon what you have. So if it's molecules, molecular, okay, then you can have London dispersion force is a possibility, dipole-dipole forces, and hydrogen bonds are all possibilities. Okay? And if you have a covalent network in which not only do they pack, but they make bonds to each other, okay, then the forces between molecules is a covalent bond itself. You can have ionic bonds, where all of the ions are positive and negative, and then you have electrostatic attractions. We call that ionic bonding. And in the last one, metallic, there are atoms that are there, and we get metallic bonding, which is totally different. We'll talk about that again. But if I take a look at molecular, they tend to be fairly soft, have low to moderately high melting points. They don't conduct electricity. They don't conduct heat. Covalent networks, very hard, very high melting points, and they don't conduct heat nor electricity. Ionic bonds, hard and brittle, very high melting points typically, and they don't conduct heat or electricity. Even though they have ions, they're bound together, they don't get to flow, and so no electricity flows. Metals, on the other hand, soft to very hard, low to high melting points, they conduct electricity and thermal energy because of the electrons, how they bond, and the electrons can flow and carry this energy, both electrical and heat conduction. Covalent network solids, something like this, you can actually see have a regular repeating structure, but there are shared electrons between the atoms. An example is diamond. Diamond is one form of how carbon is found, and so it is what's called an allotrope. And so diamond, the carbon bound together, and for every carbon there's one above. It's in a tetrahedral arrangement. Very, very hard. One of the hardest substances that we know, and its melting point is and boiling points are very high. Now, a solid molecular compound can be held together without covalent bonds. And here is another allotrope of carbons called graphite. It's a combination of covalent and basically van der Waals forces holding it together. Okay, graphite. It's what's in your pencil, right? You put the pencil on a piece of paper, you move the pencil down, and what is left on the piece of paper? You actually leave a streak of graphite. The pencil is left on the paper. That's how we write. How in the world does that happen? Well, there are covalent linkages that hold sheets of graphite together, but the sheets are stacked upon one another, and all that is held together between those sheets are van der Waals forces. Very, very soft, and just the physical moving of the pencil can shear or break those bonds, and you leave sheets of graphite on a piece of paper. And so this is where I don't have a dipole-dipole, I don't have a hydrogen bond, all I have is London dispersion forces for graphite because it's only carbon, and that is the weakest. Molecular solids can also pack in several ways, okay? And so there is hexagonal close packing and cubic close packing. And so what's the difference? Okay? The difference is this. I have level A. Well, I can't even see that. I have level A, and then I have a level B, and then I have a level A, and then I have a level B. Okay? And so they alternate A, B, A, B. Here, I have a level A, then I have a level B, then I have a level C, and then A lines up perfectly where A was before, and you repeat the pattern A, B, C, A, B, C, A, B, C. This is as close as you can get molecules together when they pack. Okay? Now, this mimics or looks like ionic bonding, but this is a molecular bonding, and this is as close as they can pack. If you actually take either one, the hexagonal close packing or the cubic close packing, they all pack in what's called the face-centered cubic version, and so we can use that unit cell for the types of calculations. Now, what's important about this? Something called the coordination number, meaning that if I'm a little molecule and I'm packed this way, how many neighbors do I touch? Okay. How many entities do I interact with? Both structures have a coordination number of 12. They touch 12 other molecules when they're packed this way. Okay. And so, if by chance you had a solid of benzene, toluene, and phenol, these three molecules, okay, benzene, toluene, and phenol, all right, what in the world are we seeing? Which one has the weakest interaction between itself? The weakest IMF, intermolecular force. And how would you know?
Would it be the benzene?
Not benzene. Look at the melting point.
Excuse me.
the least amount of energy. Boiling point is the most amount of energy. Toluene will melt first, and it melts significantly different, 100 degrees below benzene. Okay? Now, let's go back and take a look just for a second. Benzene, what kind of, what does this mean? You probably need to know that. We did see this before. Carbon, 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 that, and then we have this. But those double bonds can move around. That's why there's a circle. Okay, and then we have hydrogens on each one of them. So that's what we see in that ring. Carbons and hydrogens all around. So benzene, what is the types of intermolecular forces can it have? Can it have an ion dipole? Yes or no? No, there's no ion. Can it have a dipole-dipole? Yes or no? Is there a electronegativity difference between carbon bound to carbon? No. Is there an electronegativity difference between carbon bound to hydrogen? By definition, we said what? No. So this is all nonpolar. Can we have a hydrogen bond? No. So the only force that we can have is what? London dispersion force. Okay, what about toluene? Can we have an ion dipole? Can we have a dipole-dipole? No. Can we have a hydrogen bond? No. Can we have what? London dispersion force. Okay. Now, if I compare those two London dispersion forces, we can see by the melting point that toluene has a much lower interaction amongst itself. Why in the world would you think that it has a much lower? And when we think of London dispersion forces, there are two things that influence it. One is size. The larger it is, the better interaction you can have. And the other is what? How what? The molecular shape, how close you can pack them together. Which one of those two is really influencing this most? That carbon on the end does what? Yeah, it messes up how you can pack them. They can't get as close to each other. If they can't get as close to each other, that means they have less interaction. They have less interaction. That means it's easier to break it, and we'll see that by its melting point. Okay. All right, so having something stuck out versus that one that's round can pack pretty well. All right. Now, phenol has something sticking out also. So it can't pack as tightly. It can't get as close together. But look at its melting point. What do we see? It's really high compared to the others. Why is it really high? Not just the oxygen. What is it? You can have a hydrogen bond because it's an oxygen bound to a hydrogen, and if I complete the Lewis structure, I have two lone pairs, then it has the ability to hydrogen bond. It can't pack as tightly, so London dispersion force is lower, but it has hydrogen bonds, and hydrogen bonds are much stronger than the London dispersion force. And so that overcomes. Oh, and here's the AB, 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 or the ABC, ABC. Okay? Now, when you're in ionic crystals, the strengths of the bonds are dependent upon how much charge is there. The larger the charge, the better the bonding. And the size. The smaller it is, the stronger it is. We actually calculated this before when you looked at ionic bonding and we put them into an order on an exam. And most of you got that exam question right when you took the exam then. If I gave it to you again, okay, remember what the equation was? It was something like this. The energy equaled some sort of constant number times Q1 times Q2 divided by D. And the Q is the amount of charge. The larger the charges are, the more energy you get. And the smaller the distance is, or the smaller the size of the ion, the more energy you can get. Metallic solids usually pack hexagonally or close cubic body center, coordination numbers of 8 or 12. And so they pack really, really tightly. The bonding is different. We don't share electrons between the nuclei that are trapped between the nuclei. The nuclei have electrons that are flowing freely through the entire course of all of the metal. And so they share much, much more numbers of electrons, but a little bit weaker for each of them because the electrons can actually move from atom to atom. On average, they average out. And so metallic solids are a little bit different in terms of the idea. Now, the bonding is larger than just London dispersion force because there's no electronegativity difference. But they are not. There's not enough valence electrons to have true covalent bonds. We just have electrons flowing through the whole system. Coming back to the unit cell itself, look, we do a cartoon up here. We do a cartoon right here where you can see 1, 2, 3, 4, 5, 6, 7, 8. Okay? But what it really looks like is this. Okay? For every atom or entity that is on a quarter, there is 1/8 of it on the inside. And so something that is packed primitive cubic has 1/8 of an atom on the inside. For every corner, there are 8 corners. That represents 1 atom inside the box. That's pretty good packing, but there's a whole lot of space left in there. For the body-centered, the one that is on the inside right there, all of it is inside. And then you have an 1/8 plus 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 an 1/8. So you will have, in totality, 2 atoms inside the unit cell if you're in a body-centered configuration. A face-centered configuration, the tightest packing that you can get. You need to be able to count these. Take a look at each of these ones on the face. There is half an atom inside the box for each one that's on the face. So the top and the bottom, a half and a half. The front and the back, a half and a half. The side and the side, a half and a half. And so you have 3 inside the box from the faces, plus each one on the corners, an 1/8 times 8 of them. So you get a total of 4 atoms, or 4 molecules, inside the box in a face-centered cubic. That's as tightly as you can compact atoms inside a unit cell. So, if you take a look at this, how many atoms are in each of these? All right. For the sodium and chloride, what kind of packing do you have when you look at that? All right. Go ahead and work with your partner and try to figure out how many atoms are inside this box of each one of them. Look, discuss, look.
multiple 12 to 1 4. So it's version 3 sodium atoms. And then if you look at the chloride, there's 6 phases. So multiply 2, 1 half of that. So 3 plus, since there's 8 quarters, we multiply 8, so
All right, so what did we come up with? How many are inside? How many sodiums? No, let's see. How many chlorines? Let's do that one first.
4.
There are 4 chlorines. How many sodiums?
3.
Okay. But sodium chloride is, for every 1 sodium, there's 1 chloride. If there are 4 chlorides, how in the world do you have 3 sodiums? That is a good question. What are you missing? You see 3 chlorides right on the edges. What is the one that you're missing? Remember, every time there's a chlorine, there is next to it a what? A sodium next to a chlorine, next to a sodium. And so we see that. Chlorine, sodium, okay? You said that there was 1 chlorine right here, right? A half. And then on the bottom there's what? A half. But you have a chlorine next to a chlorine? What must be in the middle?
Sodium.
A sodium. How much of it in the middle? An entire one. Where you get 4 chlorines and 4 sodiums. Now it's hard to pick that out. Okay? If we use big space filling models that take up that entire space, you don't see that one in the middle. That's why we use those little spheres on the edges so that if there was one in the middle that you'd be able to see it. Most likely, if I do a question like this on the exam, I'm probably going to use the small one so that if there's one sitting in the middle, you should be able to see it. Okay? Like this. Okay? How many cesiums and how many chlorides are in this one? There's 1 cesium and there's 4 chlorides. Chlorides are the big ones, right? All right. Now, we can determine the empirical formula of ionic solids by determining how many ions are within that unit cell. So we said there were 4 chlorides and 4 sodiums. So the empirical formula is not 4 to 4, it is 1 to 1. All right. A, B, and C. Figure out what the empirical formula is from these drawings. Now this is a whole lot better, right? Because you can actually see what would be in here. So I want A, I want B, I want C. All right, which one do you like best on this? The first one, right? First one's easy, isn't it? So, the gray ones, how many cesiums are there? One, sitting right in the middle, right? There's one cesium. And how many chlorines? 8, because 1/8 on each of the edges. All right, next one. How many sulfurs are there? There are 4 sulfurs, right? Because it's face-centered. Each corner has an 8, so I get 1. The face, top and bottom, that's 1. Side to side, that's 1. And front and back, that's 1, so 4. So I get 4 sulfurs. And 4, oh yeah, that's 4 sulfurs. How many zincs? There are 4 zincs. All of them are inside. So what is the empirical formula? Okay, the ratio is 1:1. All right, last one. Calcium. How many calciums? 4 calciums. That's face-centered. The corners make up 1. Top and bottom make up the second. Side to side make up the third. Front and back make up the 4th. And fluorines. How many are there? 8. What is the empirical formula of that? CaF2. If I ask you to make calcium fluoride, calcium becomes what charge? Fluorine becomes what charge? 1 negative. Can they 1 and 1 come together and be balanced? No, then we do what? Crisscross calcium fluoride. And so we can check that. That works out. Okay? Could you do this on the exam? Should you be able to do this on the exam? Are you going to do this on the exam?
No.
What? Don't talk yourself into missing points. You can do it. I believe in you. You can do it. Okay? And so some of these can get complicated, but here's the arrangement, okay, of how they can work together. And so calcium fluoride, zinc sulfide, cesium fluoride, sodium fluoride, all arranged, okay? The type of packing and arrangement. So there are a whole bunch of ways that they can pack. All right. So how in the world would you approach something like this? The geometrical arrangement of ions in a crystal of lithium fluoride is the same as that of sodium fluoride. The unit cell of lithium fluoride is 4.2 angstroms on an edge. Calculate the density of lithium fluoride. Okay? All right. Density is what units? Okay, for solids, it's grams over cubic centimeters, or cubic centimeter is exactly the same thing as a what? A milliliter. Okay? I'm going to go with cubic centimeter because that's easier. Okay. What do I know about these things? This one right here. What do I know about this cubic or face-centered packing for lithium fluoride? Do I know anything?
The ratio.
You know you have a ratio to 1:1. Okay? But we don't need the ratio of 1:1. We need to know how many atoms are inside that. Okay? And we need to know its volume. What's the thing? Do we know its volume? No. Can we calculate its volume?
Yes.
Yes. So we need a volume and we need a mass. Okay? Volume is this. We have an edge. How do you get a volume from an edge? You cube it. And if you cube the number, you've got to cube the distance. Oh. All right. What else do we know? Go back to sodium chloride. How many sodiums and how many chlorides were inside when we counted that up? A couple slides ago. Okay. Well, oh, good night. We're going to have to go back. Well, they were how many? We calculated 4 sodiums and 4 chlorides. This packs exactly like that. How do I know? Because the problem said it. So, how many lithiums and how many fluorides do I have in them? I have 4 lithiums and 4 fluorides inside that. That's number of things. Okay. Number of things to a mass. What can I change number of things into? You can change them into dozens. Does that help you? No. You can change them into what? Moles. So if I have 6.022 e to the 23rd lithium fluorides, I would have 1 mole of lithium fluoride. Now, why in the world do I want to get to mole? Because I have to change the top into what? Grams. And do you have a conversion factor that goes from moles to grams of lithium fluoride? 1 mole weighs what? The molar mass. And so, come over here, chemistry reference. That's there. I want the reference. And I want a molar mass calculator, which is really the periodic table. And I go and I put lithium and I put fluoride 25.39. 939. What? I lost it all. That is a booger. Okay, 4 lithium fluorides in 4.02 cubic angstroms. 6.022 e to the 23rd lithium fluorides is 1 mole of lithium fluoride. And 1 mole of lithium fluoride is so many grams of lithium fluoride. If I remember, 25.939 is 1. Check this out. I've got grams on top. I now have grams per cubic angstrom. Is that good? No, it is not. Because I have to have a density in what? Grams per cubic centimeter. All right. Can you remember cubic angstrom can be changed into cubic meters? How? 1 angstrom is 1 e to the minus 10. But that has to be cubed. Okay? I now have grams per cubic meter. Is that good? I've got to get grams per centimeter. So cubic meter to cubic centimeter. 1 cubic centimeter is 1 e to the negative 2. But what do I have to do to that number? Cube it. And I will cancel out cubic meter. I will cancel out cubic angstrom. I cancel out numbers of lithium fluorides, moles of lithium fluoride, and I get grams over cubic centimeter. All right? What I did was I put how many were inside the box. I divided it by what the volume of that box is. I changed the numbers of things to a weight. To do that, I had to get to moles. But wonderfully, I have a conversion of numbers of things to moles. And then I did a very simple conversion of cubic angstroms to cubic meters to cubic centimeters. We did cubic things a long time ago. Okay? Now, the hardest part of this is putting it in the calculator correctly. Okay? Making sure you put them in the calculator correctly. And so, does anybody even have a guess about